recognize that, ladies, on the second practice problem that only half of it we covered, not the second half of how to do it. So B and D, no doubt you probably have difficulty with that. So we're looking at C as an example of how to do what we did cover in class. We did cover how to do this. We're going to come up with a chemical formula for the molecule known as magnesium oxide. So first thing, looking at magnesium oxide, what can I write on the board? What do I know? Well, I know I've got magnesium in this thing, right? So I've got some combination of magnesium and oxygen. Now I'm going to write this as O, but you're going to learn very quickly that that's wrong. And every time you see O by itself, you're going to go, that's not right. It should be O2. We'll find out today why that is. But magnesium and oxygen. Magnesium and oxygen are the two building blocks that make up magnesium oxide. Question is, what is their chemical formula? We're going to assume that it's ionic because that's all we've covered so far, but let's make sure. Is this ionic or covalent if these two things react? Because a metal and nonmetal. Good. So it's ionic bond, a metal and a nonmetal, meaning I've got a metal that wants to give up electrons, I have a nonmetal that wants to receive electrons, and so it's something in their charges and the balance of their charges that's going to tell me how they combine together to form magnesium oxide. So, next step, what am I going to do? Let's go to the periodic table and figure out what do these elements want to ionize to become? What ion charge do they want to have? So magnesium, let's find it over here. We see it's a column 2 element, meaning its valence electrons are in the S1 and S2 position. Does magnesium want to lose 2 or gain 6? Lose 2. If it loses 2 negatives, what does its net charge become? 2 positive. It loses 2 negative electrons. It was neutral. Now its net charge becomes 2 positive because it lost 2 negatively charged electrons. Oxygen. Oxygen is a column 6 element. Does oxygen want to lose 6 or gain 2? Gaining 2 because it's a non-metal. It wants to gain the 2. That's why magnesium and oxygen team up and say, whatever it is, magnesium wants to lose electrons, oxygen wants to gain electrons. Cool, we can work this out. But what's the exchange rate going to be? Oxygen wants to gain 2 to become 2 negative. Everybody with me so far? Okay. So the shortcut method of figuring this out is ultimately the charge of your new molecule is going to be neutral. No charge, which means the negatives have to balance the positives. Normally what we would do is ignore the charges. So I'd erase that. And then we would subscript by crossing the superscripts to make it Mg, strictly by process, Mg2O2. However, we reduce this to the least common factor. If it was 2 and 4, it would become 1 and 2, for example. In this case, it's 2 and 2. We're going to go ahead and assume that we can reduce that down to 1 and 1. And it should have been, when you looked at it this way, 2 positive and 2 negative, they balance each other out. You take one of each, boom, there's a net 0 charge. It's a neutral molecule. Okay? There are such things as hydrogen peroxide. We've got water, which is H2O, and hydrogen peroxide was H2O2. But in those cases, we're talking about covalent molecules. In those cases, we have more than one way that we can combine, and this crossing method doesn't work. Okay? In the crossing method, for figuring out the formula, it only works on ionic compounds. And they can only combine in one distinct way, which is why Mg2O2 would reduce down to Mg1O1. We don't write ones, they're implied. So it's just MgO for magnesium oxide. Now you couldn't do question 2, I think it was B and D, because they deal with the exceptions on the ionic compounds, and we're going to deal with the exceptions right now. So these are the exceptions that we've talked about, where I've said, now when you're looking at the periodic table and you find you have an element that's in this range here, it's in the D block. They don't behave according to nice simple rules, and you're not going to have a lot of compounds that deal in D block, because frankly, I and the authors of this text are much more concerned that you understand how to get to the valence configuration using the S and the P block. Remember too that when you're filling the D block, it's always one energy level lower than the P's and the S's that it sits between. Remember that? Like when we read across 4s2, 3d, it's one energy level lower. So when you're talking about the valence electrons, the valence electrons for your purposes are almost always, virtually always going to be S and P orbitals, which is why they try to build to 8, because S plus P, 6 plus 2 is 8. That's where the octet rule comes into play. And again, the wording, the octet rule, says that virtually all, or mostly all elements seek to have 8 valence electrons. Not all. Because within the octet rule, there's the exceptions of hydrogen, helium, lithium, and beryllium, the first 4 elements that want to have 2. They're just looking to fill up the S1, or excuse me, the 1s shell. Or, you know, they don't want to go to 8. They just want to go to 2 in their valence. All right. The exceptions. I'm going to pick it up on 143, handling exceptions. And here they use tin as the example. Tin, atomic number 50. You can remember it's tin because it looks like sin, right? And tin rhymes with sin. So SN is tin. Just the way you remember that gold is AU and silver is AG. Why? You would assume that's gold, but it's not, so it's silver. So looking at tin, and they give you the full electron configuration in there, you can see all the way to the right that between the 5s2 and the 5p2 orbitals, by the way that they fill, that we have the 4d10 block, which makes sense. We're here at this level, 5s1, 5s2, 4d1, all the way up to 4d10, back up to 5p1 and 2. So how many valence electrons are in tin in its natural normal state? Okay. There's 50 total electrons. How many valence electrons are there? Okay. Just remember, it's sitting over here in the 4th column. Okay? 4 valence electrons. They are in the 5s and 5p orbitals. Okay? 2 in the 5s and 2 in the 5p. And you see that here on your extended configuration all the way to the right. Now here's the problem. You can see that once we lose 2 electrons from the configuration, from tin, we lose 2 electrons. Now in order of fill, we're into the D block, right? But in terms of energy level, we look back here to the 5s2. And don't get all bent out of shape about, well, why at this level of chemistry, just this is the way it is. This is the rule. So if you're losing electrons and your fill order would put you into this D block, but you know that you're actually looking at the S block, means that this element, and this is all you really need to remember about this, is that these elements have multiple ions that they can form. There's multiple ways. When I say, for example, tin, what charge does it want to have? There's more than one answer. It's not as simple as it wants to lose all the way back to 8, or it wants to gain all the way up to 8. The fact that we were talking about the transition between the 5s orbitals and the 4d orbitals, that there's some, you know, interplay between the physics that's causing them to act kind of wonky at times. I don't know why I said that. I've never used the word wonky before, but it seemed to fit, so there we go. It's whack, okay? But there are some common ways that ions that they will form. They'll tell you in the book here that there are two different tin ions that can be formed. You can form a tin 2 and a tin 4 ion. So you've got the name written out and then a Roman numeral following the name. Tin 2, tin 4. Now, tin, is it a metal or a nonmetal? Okay, and these are only going to be affecting metals, right? We're talking about everything over this side of the stair step. we start getting involved with the d orbitals that are one energy level lower, it's only going to be for metals. So you look to the metal. Metals want to take on what type of charge? Not the count, but what type of charge? The positive charge because they want to lose electrons, right? Metals want to lose electrons, so therefore they want to have a positive charge. You look over here and you say, what does the Roman numeral mean? That's the charged count it wants to have. So in this case, tin, its abbreviation is SN for sin. If I said, what charge does a tin 2 atom want to have, you would tell me it wants to be 2 positive. But a tin 4, what does it want to have? A tin 4 atom wants to ionize to become a 4 positive. It wants to become a positive, okay? But how much? How much is by the Roman numeral? What this is saying is if I have tin, I don't know exactly how it's going to combine. It's still going to combine ionically, okay? But think of tin 2 and tin 4 as two different cousins of tin. Tin 4 can only combine with other elements in a certain way, just like ionics, okay? We're not talking covalent where you can have 1s and 2s and 3s and 4s and all different combinations. It's either a tin 4 or a tin 2, and then it's going to obey the ionic rules, okay? It's going to obey the ionic rules. In a moment, we get into covalent rules, you understand the difference. So all it means is that for some transition metals, or excuse me, for some of the D block metals here, this whole transition element section, you need more information than just simply tin. A savvy young chemist would say, is that tin 2 or tin 4? Because I can't go any farther until I know what ion that tin is going to form. And if you flip the page over to 144, table 4.2, it gives you some of the most common transition metals and the ions that they form. They form more than one positive ion. Chromium, iron, copper, gold, tin, lead. Those ones are listed because those are the ones you're going to see most often. Okay? And right now, you don't have to memorize this table, I don't believe, but be familiar with it. So when you get more familiar to know that chromium is either a +2 or a +3. Why would that be? Chromium either +2 or +3. And again, that's why up here, this non-standard electron configurations are written, because this chart is trying to show different information. The way we taught it in here, you're always going to have your element, your noble gas or your inert gas, and then build up from there following the pattern. For those of you that took those things and just wrote strictly from this chart, this is a non-standard way according to our textbook, the way we're doing it. Some of these are shown in a non-standard way. Here's a 4D1 5S1 or 4D4 5S1. Okay? So, again, if you have a transition element, you're going to have to be given what ion are we dealing with. Again, in this case, is it a tin 2 or a tin 4? So, let's go ahead and do the on your own on 145. We'll do it together. You don't have to do it in advance, but let's walk through these as examples of how to use transition elements that form different ions. It says, give the chemical formula for the following compounds. A tin 4 fluoride. This is page 145, on your own 4.4. For the compound tin 4 fluoride, and that's the way you would say it. Tin 4 fluoride. Fluoride, not fluoride, fluoride. Okay. Tin 4 fluoride. Now, just like we did before with the other ionic formulas, trying to figure that out, let's go through and write down the two elements that are involved in this ionic compound. We've got tin, which is going to be SN, and we have fluoride, which is F, right? Now let's go ahead and write the charge that the ion wants to have. If I gave you potassium, calcium, anything from the column 1 and 2 over here, what charge does it want to have? You would say it either wants to have a +1 or +2 charge. Now we're dealing with a transition element, tin 4. this transition element, tin 4. What charge does tin 4 want to have? 4 plus. 4, I know it's 4 because the Roman numeral 4 tells me it's forming an ion that has a charge value of 4. Positive or negative, it's a metal, it wants to go positive. So tin has a desire to be a 4 positive ion. Now we look over at fluorine. Its iode name is fluoride, and use the same rules we've always used. Fluoride. Fluoride comes from fluorine. Fluorine is a column 7 element. So it has 7 valence electrons. It wants to have 8. It's non-metal, so it wants to get an electron. How many does it want to get? 1, so its charge would be 1 negative. 1 negative. So tin 4 and fluoride, those are the charges those ions want to have. So now the method of coming up with the formula using the shortcut is I'm going to disregard the sign and transpose these superscripts as subscripts by crossing them, which becomes SN1F4. However, we don't write the ones because they're implied. It's SNF4. All right, SNF4. The second one there is chromium chloride. Is it chromium 3? Chromium 3. Chromium 3 chloride. Okay? So chromium 3 chloride, 2 elements, chromium and chlorine. Chromium, the chromium 3 ion wants to have what charge? 3 positive. I know it's 3 because of this, Roman numeral 3. I know it's positive because it's the metal. Chlorine, it's column 7 element. It wants to become 1 negative. The formula, transpose as subscripts. This would be 1, I'm going to leave it off, and this is 3. CrCl3. You leave it off because it's 1. Technically, we write it like this, but we never write a 1 subscript because it's redundant. Because chromium is there, it has to have at least 1. If it has more than 1, we'd write 2, 3, 4, whatever, but we don't write it just as a 1. Okay, so chromium chloride is a CrCl3 molecule. That's the chemical formula for chromium chloride. And the third one, copper 2 oxide. Isn't it great to actually do chemistry now? Right? All right, so copper 2 oxide. Copper, oxygen. Oxygen is a column 6, so it wants to become 2 negative. Copper 2, it wants to become 2 positive. Bringing them down to transposing, it would be Cu2O2. However, it just becomes CuO. Correct. Because these would reduce down. They pair 2 to 2 is same as pairing 1 to 1. Okay. The greatest common factor would be 2, and they divide by 2, and they both become 1. Way to look at it. So it becomes CuO, formula for copper 2 oxide. Copper 2 oxide is different than copper oxide. Copper oxide might be copper 1 oxide. Okay? If we made copper 1 oxide, then it would be 2 to 1. See? If we made copper 1 oxide, if you look over at your chart on page 4.2, copper tends to form either a +1 or +2 ion. So if we had copper 1 oxide, then it would be Cu wants to become 1 positive, and oxygen wants to become 2 negative, so the formula would be Cu2O. Okay? And again, when you put these combinations together, the charges are going to balance out. The reason why it's 1 copper and 1 oxygen is because it's 2 positive pairing up with 2 negative, they neutralize each other. In this case here, copper has a +1, oxygen has a 2 negative. You need 2 to balance out the 2. So to get 2, you need 2 of them. 2 at 1 positive each cancels out 1 at 2 negative each for a net charge of 0. And that's why this technique of taking the superscripts and writing them as subscripts works. Now you can do this same thing backwards, and On Your Own 4.5 does that. Let's go ahead and try to figure out what is the name of the molecule whose formula is Fe, what's Fe3 or FeF3? Now we know that it's an ionic bond, so we can already give a close name for this. Not an exact name, but a close name for this. I know it has iron in it, and it has fluorine in it. So its name is going to be some type of iron fluoride. Okay? If iron only formed one ion, then it would just simply be iron fluoride. But we're savvy enough now to say, wait a minute, iron is in this wonky D area. It's not as simple as just iron fluoride. It has to be iron something fluoride. So let's go over here and take a look at it. We know from this that we can have iron, or we do have iron, and we do have fluorine to form fluoride. We know that iron, or excuse me, the fluorine wants to have what charge? It always wants to have, over here, each one of them wants to have a 1 negative charge, right? 1 negative. But since I have 3 of them, I have a total fluorine contribution of what? 3 negative. I've got 3. Each one of them, let me try to get a standard way of writing this. In order for me to get, I know, for example, that I have 3 fluorines at -1 each. Is that a better way to write it? I have 3 fluorines, and each one of them has a 1 negative charge. I know that. What's my total charge because of 3 fluorines each having a 1 negative? What's the sum of their charges? The sum of their charges is 3 negative, right? 3 times 1 is 3 negative. So if every atom is 1 negative, and I have 3 ions, then I have 3 negative total charge coming from the fluorine. So what must the iron contribute to make it neutral? If fluorine is 3 negative, the iron must be 3 positive. And that 3 positive comes from just 1 ion. See that? I only have 1 iron. And this 1 iron has to contribute the positive that balances out the negative contributed by 3 fluorides, which each are -1. The 3 fluorides at -1 each make a -3 charge. So my 1 iron has to balance that with a +3 charge. So how do I write this formula then? I know that it's going to be iron with a Roman numeral of some kind, fluoride. What charge does my iron ion want to take on? 3 positive. So it's iron 3 fluoride. This iron needs to have a 3 positive charge to balance out the negatives contributed by the fluoride ions. Mm-hmm.
So how did you get 3 negative for fluoride?
Each fluoride ion wants to have what charge? So I go over here and I say each one of them wants to have a 1 negative charge. My molecule has how many 1 negative charges? 3 of them. So 3, each of them having 1 negative, when they combine together, is a total of 3 negatives. A 1 negative plus a 1 negative plus a 1 negative for the 3 different ions is a total of -3. Now I need to balance that with whatever the charge of this is. This happens to be just one of them. So one ion has to balance out 3 negative. The balance of 3 negative is 3 positive. So iron has to be an iron 3 fluoride. Okay. Let's go ahead and do the second one there. NiI. NiI. The name of this molecule. Okay. Nickel, circled right here, number 28. It's one of those transition elements. So it's going to have a weird name. So I know it's going to be nickel something. Nickel something I. I is a column 7 element. Its name is going to be, its IDE name is iodide, right? So it's nickel something iodide. Let's go over here and look at what charges do they want to have. I can't address the nickel yet, but I know that nickel and iodide combine in a 1-to-1. What does iodide want to have? Iodide always wants to become a 1 negative. Iodide always wants to become a 1 negative. So what's my total contribution to the molecule from all of the iodide? There's only one of them. So 1 negative, right? So what does the nickel, what's the nickel contribution be? 1 positive. There's only one of them. It works out good. So it has to be nickel 1 iodide. Right? Because the net charge has to be 0. The combination of all of the iodides in this case only comes up to be -1. So that -1 charge needs to be balanced by a +1 charge, which needs to come from all of the nickels there. There's only 1. So 1 at +1 balances 1 at -1. So to give me nickel 1 iodide. Let's do the last one, and then we'll move on. Mn2O3. Mn2O3. Now we know oxygen, column 6 element, all the way over here on the right. So column 6, it's going to give us, what kind of charge does oxygen want to have? All the time? Oxygen wants to have, if I'm just looking at oxygen, oxygen wants to have a 2 negative charge. Manganese, Mn, we're not sure, right? We're not sure what kind of a charge it has yet. But let's just look at the oxygen. How many oxygen ions are in this molecule? 3 of them. So 3 times, what does each one of them contribute? 2 negative. So 3 times a 2 negative is going to give me a total of 6 negative. A 6 negative is coming from the oxygen, right? A 6 negative is coming from the oxygen. I need to balance that out with a 6 positive from the manganese. Do you see that? Manganese has to give me 6 positive to balance out the 6 negative from the oxygen. So this becomes 6 positives, but I've got 2 of them, right? So each one of them contributes, 2. Each one of them contributes 2, so therefore each one of them gives me 3. If I have 2 manganese at 3 positive each, that gives me a total of 6 positive. And if I have 3 oxygens at 2 negative each, that gives me 6 negatives, and they balance. So each one of these manganese needs to have a +3 charge. So the name of this molecule is manganese 3 oxide. It's a manganese 3 oxide. Because manganese in this combination needs to have a +3 charge to balance out the -2 for every one of those 3 oxygens. See? It's not that difficult once you get the process down, and maybe this is the clearest way to do it. These are the 2 different elements. Each one of them wants to have this charge. How many do I have times the charge it has gives me the contributions for the one I know. So I need that same charge over here on the positive sides. How many do I have? 2. Each one of them contributes a 3 positive. Manganese 3. This right here dictates that right there. Manganese 3 oxide. All right. Questions on that? Again, you may understand it, but just have to practice it. Just have to keep doing it. Okay? So, I mean, even if you did the practice problems, do them again. Just go back over them again. We'll go through the practice problems, the specific ones that you turn in for homework in a couple days. Matter of fact, you may see them again, similar, or maybe even the very same questions on a quiz coming up soon. So, let me get rid of this, and we will pick up on new material. Actually, this was new material. This was just an extension of what we did last time. Now we're going to go into a kind of a different concept altogether. For my purposes right now, I'm just going to draw a rectangle on the board because I'm going to be talking about the periodic table, and I recognize that the periodic table has little pops up here and down and across, but just for our purposes, I'm just going to draw a rectangle. Okay, this represents the periodic table. We're going to talk about some periodic properties. Now, periodic property is a property that repeats itself. You know, it happens over and over again. There's a pattern to it. It has a period, okay? So it's something that repeats. It happens consistently, all right? So we talk about periodic properties from the table. It means we can make some relationships between different elements and know how they relate to one another because this is a repeating pattern, something that happens over and over and over again. We're going to talk about 3 different properties from the periodic table. But the first thing we need to discuss is this idea of ionization energy. And what does it mean for something to be ionized? We've been talking about ions all along, right? To make an ion means to have a neutral element from which we either add or remove electrons. If you look in your book, we're on page 145, and it says, ionization is the process by which an atom turns into an ion by gaining or losing electrons. We're familiar with the concept. We've been doing it. We just need now to know that the process of becoming an ion is called ionization. So when I say that calcium wants to become a +2, that +2 happens because the element becomes ionized and becomes an ion as a result of the ionization. Okay? But the next level of definition comes down to ionization energy. And there's a nuance, a very small nuance between ionization energy and the next concept we're going to get into, which is called electronegativity. Okay? Electronegativity and ionization energy are very similar. They have to do with perspective. That's the way I remember it. The way I remember the difference between ionization energy and electronegativity is perspective. And so for this first one, ionization energy, the definition in the book, the amount of energy needed to take away an electron from an atom. Now, how much energy does it take to take something away? I want you to think of ionization energy as from the perspective of the thing that is losing the electrons, the metal. Think of it in terms of metals, okay? You're a metal. How much energy does it take to pull something away from you? Or maybe not even a metal. Think of it as because it's going to be the metal, but the ion that is giving up the electron. How much energy does it take to rip an electron away from you is a way to think of it, okay? The energy to take an electron away is a way to understand ionization energy. What we're going to find as we look at the periodic table is that there is a distinct pattern of this periodic property. Let's work from maybe the way we're used to thinking, ionization energy, the energy required to take something away from me. And if I were to say I were suddenly, okay, here's the deal. Poof, you're now a potassium atom. Can you put yourselves in the place of a potassium atom? Okay. Just pretend for a minute, from all we know, this is hyper personification, right? Before we said treat them like people. Okay, not just like people. You are potassium. Okay? Answer me this question. How hard are you going to fight to keep your electron? Your valence electron, right? You've got an S1 valence electron. How hard are you going to fight to keep it? Not very much, right? As a matter of fact, what's your real hope? Somebody please take this from me, right? So unless you're one of those people that wants to get rid of stuff until somebody tries to take your stuff, you're like, that's my stuff. Okay. But other than that, potassium pretty much wants to give that away. Calcium too. You see, potassium, it's pretty easy for potassium to say, it's so much easier to lose 1 than to gain 7. I'm not up for that fight. Please, take my electron. Calcium has an S2, has 2 electrons in that orbital. Calcium has the same kind of dilemma. It either needs to lose 2 or build 6. But if you think in your mind, which is easier? To get 6 more or to get 7 more? Well, it's harder to get 7 than it is to get 6. But it's still a pretty easy choice for calcium. It's not as easy a choice as it is for potassium. Potassium's like, yeah, take it. Just go. Just go. Calcium's like, yeah, go. But if I happen to have 6 more, I'll take it, but it's not going to happen. So here, go ahead and take my electrons. Here's the point. As we move from left to right, do you see, even if you just think in terms of metals and nonmetals, that the metals are trying to give them away and the nonmetals are trying to get them? Okay? So how hard are they fighting to keep? These guys don't want to keep hardly at all. These guys want to get more. So what are they doing? They're protecting what they have, right? They're going to start by protecting what they have, and they're going to try to get more. So if you think in terms of you being an individual atom up here, thinking about how hard are you trying to hold on to something, that means that whoever's trying to take it from you needs to exert more energy than you're using to hold on to it. And that's the way I like you to think about ionization energy. How much is that atom trying to hold on to it? Metals, not very much. And I'll write it this way. I'll use a small I here for ionization energy, okay? As I move from left to right on the periodic table, as I go from metals to nonmetals, does the desire to hold on to my electrons increase or decrease? Does my desire to hold on to my electrons increase or decrease as I move from left to right, from metals to nonmetals? My desire to hold on to what I already have. It increases, right? Okay. Sodium is not going to try very hard to hold on to that electron, and chlorine is not going to let anybody go because it just needs one more. If it loses one, now it's going to find 2, right? So, as we go from left to right, the ionization energy, the amount that it takes to steal from me, increases. It increases as I move from left to right. As I go from potassium, doesn't take much. Compared to bromine, you're not taking anything from bromine. Bromine is holding on hard, okay? Now there's another trend as well. As we look at the periodic table, up and down. The ionization energy. How hard is something, how much energy does it take, or how hard does that element hold on to its electrons? And for right now, I'll just give you that pattern. It goes from, it increases as you go from bottom to top. Part of it has to do with down here, think about this, how far away are the electrons getting from the nucleus? I mean, up here, 1, 2, 3, 4, I mean, these electrons are relatively close to the nucleus, right? As you get farther and farther down here, you're building up more and more electrons farther and farther away. The ability to hold on to those, to hold on to them, decreases. Because the electromagnetic forces that hold them together are farther out. I mean, they're just farther away. It's harder to keep track of those things that are far away than those things that are close. And so the energy required to snatch an electron that's way far away from the nucleus, it's a lot easier than it is an electron that's close to the nucleus. And so the trend is ionization energy increases as you go up and increases as you go to the right. So as you go up and right, ionization energy increases. Now, most of the time you're going to be asked a question about which one has a greater ionization energy. They're either going to be 2 elements that are in a column or 2 elements that are in a row. So in terms of ionization energy, if you have given 2 elements that are in a column, which one has a greater ionization energy? The higher one. If you're given 2 elements that are in a row across, which one has more ionization energy? The one farther to the right. Which means that element is going to hold on to its electrons. It's harder to get them away the higher the ionization energy. All right? Now we're going to superimpose one of the next periodic properties on here, and that's electronegativity. Electronegativity takes that same understanding, but rather than looking at it from the position of the atom which is becoming ionized by consider how strongly it's holding on to the electrons. Think of it in terms of how strongly it's trying to get other electrons. It's slightly different. It's not exactly the same thing, but it's very much akin. Like I said, chlorine is going to fight really hard to get, but it's also going to fight very hard to keep. Because losing electrons is like, you need to keep what you have if you need to build. Keep what you have and grab more. Ionization energy looks at chlorine and says, how hard is chlorine holding on to what it has? Electronegativity says, how hard is chlorine trying to take from somebody else? Okay? Again, they're very related, but they're not exactly the same thing. And the trend on the periodic table is exactly the same as it was for ionization energy. On page 148, it says electronegativity is a measure of how strongly an atom attracts extra electrons to itself. Electronegativity is basically the force used to steal electrons or to get electrons. Ionization energy is the force used to hold on to what you have. And the trend is from same trend as this. So we might put an E down here and a E here and a E here. So as you go up the periodic table, the electronegativity increases. And as you go from left to right, the electronegativity increases. What does that tell me? Over here, helium, neon, these folks over here, they have an incredibly high ionization energy. Okay? They're not letting go of anything. They have a very high electronegativity. They're using a lot of force to get what they need. Right? Hydrogen's already satisfied. Let's use fluorine as an example then. Fluorine. Fluorine is both fighting very hard to keep what it has, and it's fighting very hard to get one more. And because of the same reasons, the trend is downward. So as you go look at a column, the higher element on the table in a column has a greater electronegativity. It is exerting more force to get an electron. And as you move left or right in a row, the one to the right is exerting a greater force to get another electron. This idea of electronegativity is very important when we get into covalent bonds, which we'll probably pick up on Monday. So just from looking at the table, this idea of greater or lesser than ionization energy or electronegativity. Now the third periodic property that we're going to look at is atomic radius. The idea of atomic radius kind of makes us put away the quantum mechanical model for a minute and go back to a Bohr model. But it's basically the idea of how much space does an atom take up with all of its orbits, all of its orbitals. Okay? So if you think of, it's probably easier to think about this one as if the atom were a solar system, like a Bohr model, with the sun in the middle as the nucleus and then planets orbiting. How big is that structure going to be? Okay? And what are the trends? This one is a little bit different in that, let's do the vertical part first. In terms of radius, it should make sense that if I have I'm going to use a different chart just so ionization energy and electronegativity follow the same pattern. Now we're talking about a radius. Does it make sense to you? Do you know a trend? Can you tell me a trend about moving from top to bottom in terms of radius? Which atom would be bigger than other atoms in terms of up and down? Does it make sense to you that if I've got a nucleus, if I'm helium, or hydrogen, excuse me, I've got one proton, I've got no neutrons, I've got one electron, how much space do I take up? Virtually nothing. But if I'm down here and I've got a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4, how much space do all those electrons need? A lot of space. So moving from top to bottom, the radius of the atom increases. It's like taking a solar system and adding more planets. My radius goes from a radius here to a large radius going from top to bottom. As I move down a column, the radius of my atom becomes bigger. Make sense? Now, the one that's kind of counterintuitive is this one. I'm going to tell you right now that as you go from right to left, the radius actually gets smaller the farther to the right you go. Now, why would that be? That sounds different too, because as we go from left to right, we're adding electrons. Why would its radius actually be getting smaller? And the principle is like this. When we're going from top to bottom, we're adding energy levels, right? We're adding more distant energy levels. As we go from right to left, yes, we're adding individual electrons, but we're not adding extensive orbitals. What we're doing is we're adding more electrons to the same orbitals. And every time we add an electron, we're also adding a proton, which means we're making the nucleus more concentrated positive. And so as we add those electrons in the same orbitals as others already exist in, the greater positive charge from the nucleus is pulling harder on those electrons, causing it to actually get smaller as we add electrons. Because we're adding electrons, but we're also adding protons. But we're staying within the same orbitals. When we move this way, up and down, we're adding protons, but we're expanding the orbitals. Okay? So the trend is, and this is the little nuance, as you move from right to left, the radius increases, which means as I fill the orbitals and go this way, the radius is actually getting smaller. But then as I move down to the next row, what happens? Boom, another energy level. And then I fill that energy level. And then boom, another energy level. And then I fill that energy level. And then another energy level. And I fill that energy level. Okay? So it has this kind of expanding, contraction kind of thing as we go from top to bottom, left to right, in terms of radius. So these two, these are important for you to know, be able to kind of recreate for your own notes and for tests. Hey, electronegativity looks like this. The radius here actually does, this is the positive trend for the radius. Down and left is positive for the radius. Up and right is the trend for ionization energy and electronegativity.